So, welcome back, students. Now, we have been through with the basic framework of analysis of variance for one way. And when we were discussing this one way ANOVA, I told you that I will be taking up the model later on. Because once you are through with the example, it will be you will be able to understand the intrinsics of this model. Okay, so now I will take around 5-10 minutes to discuss about that on which model this ANOVA is based. Okay, so in one way ANOVA, the response variable y, okay, that is we have a response variable y as there was the yield of shrimp we have discussed already. Okay, demonstrated in the following one-way table in which there are r rows, means rows we are taking the treatment, and c columns in which we takes the observations. Okay, so basically this ANOVA, let me not make this like this, so it will be one thing, right? So basically there are level of factors. So there we have discussed about three temperatures. We can take four temperature, we can take five temperature, or sometimes we can take say for example rations. Okay, different level of proteins. We can take doses in pharmacology. We can take certain exercise, effect of exercise on the heart rate of the patient in case of physiology. Okay, so you quote any subject, there is the application of ANOVA, because here what you are seeing that we are not simply comparing the measures of central tendency or measures of dispersion, but here we are comparing the cause, that is the factors, that whether these factors have a significant effect on them. Okay, because here everything remains the same in this levels, but only one thing differs, that is here in our example in shrimp yield the temperature was different. Okay, so and that effect of that temperature on that group, the variation caused by that temperature is being taken out by the ANOVA into a separate row. Okay, that is the assignable causes. And rest of the variation in the data, which is due to within the group variation, that remains in the error component. Okay, and all this assignable and non-assignable variation constitutes your total variation. Okay, so basically there are these are rows of the treatment and there are number of observation. There we have 3 observation in 3 tanks. Okay, but we can have 4 tanks, we can have 5 tanks, 10, 11, 12 maintained at the same temperature. Okay, so those tanks were nothing but the replication, isn't it? Okay, so when these were the replications, what we have to do in one way ANOVA is that we have to total them up. Okay, that is we total them here, then total the second row, total the third row, likewise you total the rth row. Okay, and then you have to take the mean. So these mean will be used when you will be doing the pairwise test. Once you have this total, okay, then you make the square table. Okay, from the square table then you have to calculate total number of observations, which you can calculate by rows into columns. Okay, then you have to calculate the correction factor from the grand total, because in this only you can make the grand total here in this table. Okay, grand total is square divided by n. Then once you have the grand total, then you from the square table you can have the row sum of square. From raw sum of square, you can have the total sum of square, that is the raw sum of square minus correction factor. Okay, then you can have the sum of square due to treatments, right? That is the square of these totals divided by how many these columns are there, that is making this. Okay, so if there are c columns, then divided 1 by c. Okay, so this is how we calculate the treatment. This is sum of square due to treatment, and rest of the thing is assigned to the error, that is uh, whatever you got in the treatments, sum of square due to treatments or assignable causes, you subtract that value from the total sum of square, so you get the error value. Okay, and then we make the table, right? So basically at this table I have described to you. okay, in our last uh, session. So basically, what is the model on which this ANOVA is based? The model for one-way analysis of variance is that your response is depend on a mean for each level of a factor plus error term. Okay, that is, this factor can estimate this response, but with some error term. Okay, so this Yij is equal to the mean of that group plus Eij, and this mean of that particular row, this can be rewritten as total mean plus mean of that row minus total mean. So this will cancel out, so this remains the same plus Eij, and this is but nothing but the alpha, that is the deviation from the original or the population band. Okay, so this is the factors alpha here. So this basically what we are estimating this Yij is from the row mean. Okay, and if these rows differ from each other, that is what being calculated in the ANOVA, right? So this is how we calculate this one-way ANOVA. Now we will extend our knowledge of one-way ANOVA towards the, if say for example there are two factors are there, okay, then what will be, right? So let us start our two-way ANOVA now. So in two-way ANOVA, uh, what we have studied in one-way ANOVA, we have considered the case where you had only one categorized independent variable at different levels. Okay, different levels on there. So now in this particular unit, consider a case with two categorical predictors. Now if we have two predictors instead of one, now we will be having two predictors, then we have to conduct the two-way ANOVA. If we have three predictors, then we have to conduct three-way ANOVA. If we have four predictors, then four-way ANOVA. So we will do up to two-way ANOVA. So in general, sometimes you have more than one categorical predictor variable at a different level and a continuous response variable, then it is called two-way classification, right? So in two-way ANOVA, we divide the total source of variation into two components. First will be the source of variation due to first assignable factor, okay, that is factor 1, variation due to factor 1. Then source of variation due to second assignable factor, okay, and then within group or due to the error. Earlier we were having only one assignable factor. So we were telling that as due to assignable factor and non-assignable factor. Now it is first assignable factor, second assignable factor, and within groups. Now what will be the model? So now your factor on one side, this will be the treatment and this will be your second factor. Instead of number of observations simply, this will be your second factor. And when you were totaling it on this side only, because your treatment were on this side, now you will be totaling on the below also because of this factor. And similarly, when you were calculating for this treatment, the sum of square due to this factor, second factor will also be calculated. How to do that? Let us see. So here the response depends upon the mean for each level of factor. Okay. So whatever you will be getting on this side, the deviations from the total mean you will be getting on this side is designated as alpha. And the deviation from the overall mean you getting on below side, these samples will be designated as beta. Okay. So here these will be two things instead of simply alpha, this will be alpha and beta. And there will be one more component, their interaction. But because there is only one and one observation in each block, if this could have been more number of observation within here, then we could find the interaction also. But in this case, this interaction will be 0. So this will simply be equal to Yij will be equal to mu, that is the population mean, that is alpha I, beta j, and errors due to I and j. Okay. So what will be, these will be your basic assumptions, that all observations are independent, Yij, different effects, that is effect of level of factor A and effect of level of factor B and error effect are additive in nature. That is what our model are there. That is, these all are additive in nature. Okay. Then Eij are independently and identically distributed normally with mean 0 and variance sigma e square. And there is no interaction between the level of factor A and level of factor B. Then we will be doing this fixed, and that is why this is also known as fixed effect ANOVA. Okay, ANOVA. That is, our factors are fixed; those are not random, neither mixed. Okay, so this is fixed effect, and there is no interaction, right? So first will be our there will be, because now there are two factors. So we will be having two hypotheses. First hypothesis will be for first factor. Second hypothesis will be for second factor. So our hypothesis, null hypothesis for A factor and null hypothesis for B factor. So for first factor, the deviations will be considered to be 0. That is, there is no difference in the deviations. And for second factor also, the deviations are considered to be 0. That is, there is no deviation from the mean. So overall mean. So now we will try to understand the general procedure for testing the hypothesis using this two-way. Okay. Now deliberately I am using the same example which is has been used earlier, but that example was for one way alone. So now see that how the things can change, and the same thing you have to apply the two factors also. Okay. So in investigation quoted in previous example, an expert panel suggested investigator to check for salinity level in three tanks. Okay, as it is supposed to affect the shrimp production. So there is some expert panel, this investigator went to them and told that I have got these results and I have seen that the temperature is affecting this shrimp yield, and these were the pairwise tests. So that panel suggests that whether you have checked the salinity in the each tank you were observing. So he said, no, I have not taken into consideration. So they told that salinity affects this shrimp production. So just you see that what is this salinity level in tank 1, tank 2, tank 3. Okay. So this then he investigator found that there was difference in the salinity of water used in three tanks. So tank 1 salinity was 700 ppm, then tank 2 salinity was 1400 ppm, and tank 3 salinity was 2100 ppm. So there was a difference, and this salinity was almost 3 times the salinity in the first tank. So now he redesigns the ANOVA into two-way to partition the effect of salinity in the experiment. Okay. So now how we will be doing this? Okay. So again, we will be making the this classification. Okay. So basically here this part we have already done, but this part we haven't done. But because there is the difference in the salinity in each tank, so we will also be totaling the columns. So for column 1 this will be 30, for column 2 this will be 36, for column 3 it will be 33. And this, of course, this will be total will be 99, and we will also be finding the mean of the three columns, that is at three salinity level. So first one was 10, another was 12, and third one was 11. Now we will be setting up the hypothesis. So first hypothesis will be for the temperature, and second hypothesis will be for the salinity, right? So in first hypothesis, the null hypothesis will be that there is no difference in the yield due to the temperature. Then second, for second factor, there is no difference in the yield due to the salinity. So these will constitute our null and alternative hypothesis. Now we will be making the square table as we have made earlier. So we got these values, okay, from the square table. So this is 1401 remains the same, right? So total number of observation remains the same. Sum of the steps remains the same. Grand total remains the same, and your correction factor remains the same. Even your raw sum of square also remains the same, and your total sum of square also remains the same as it was with the one-way ANOVA. Your sum of square due to temperature will also remains the same as we have calculated earlier. Now a second thing will come into account is sum of square due to salinity. So what we will be doing? That is, we will be squaring the values you got as a total in the each column. That is, what are the values you got in each column as a total? So it was 30, 36 and 33, and these values were comprised by three values, these three values, and then these three values. So basically these 30 square, 36 square and 33 square divided by 3. So it came out to be 6. Okay. Now sum of square due to error will be total sum of square minus sum of square due to temperature and sum of square due to salinity. That is the first factor, assignable factor, and then the second assignable factor, right? So basically here your this will be equal to total sum of square were 312 minus 294 minus 6. So it will be equal to 12. Now we will be setting up the ANOVA. So let me show you that how this ANOVA is made. Okay, let it be on the next page. So this is your ANOVA table, right? So I will just describe that how the things will change in this ANOVA. So your sources of variation, in your sources of variation, so your first was temperature, it was earlier also. Now a second factor has been introduced, and that is your salinity. Okay, and third factor was same as it was earlier, it is error, and then this is the total, right? So now in temperature, number of rows minus 1, it will be equal to 2. Then in this salinity, that is the number of columns minus 1, that is 3 minus 1 is equal to 2. So its degree of freedom is also 2. Now this particularly this will be equal to n minus r minus c. So it will be equal to sorry, not n minus r minus c. Let me first find out that what it will be. So it will be total, that is n minus 1 minus r minus 1 minus c minus 1. So it will be n minus 1 minus r plus 1 minus c plus 1. So this will cut out. So this will be n minus r minus c plus 1. So this will be our degrees of freedom, n minus c and then plus 1. So this will be 9 minus 3 minus 3 and plus 1. So it will be equal to 4, and this will be n minus 1 is equal to 8. Okay. Now this part we have already discussed in analysis of variance for one way. Okay. This remains the same. Now sum of square due to salinity was calculated to be 6, isn't it? So when these sum of square due to salinity was calculated to be 6, so mean sum of square due to salinity will be sum of square due to salinity divided by column minus 1. So it will be, that is the degrees of freedom due to salinity. So it will be 6 by 2 is equal to 3. Now this f value due to this salinity will be mean sum of square due to salinity divided by mean of sum square due to error. So now in error, your degrees of freedom has changed. Earlier it was 6. So 2 degrees of freedom has gone into salinity. So now these are 4. So this 12 sum of square due to error, because earlier this if you see, when we were not considering this salinity, right? So this was in our error, that is we were not knowing that out of that 18, if you recall this your earlier table, so if you recall this error component, so this error component was 18. That is the sum of square ascribable or the variation ascribed to unassignable causes. So when you assigned a cause and classified that into the table as salinity, so 6 value has been removed from it. Now it has become 12 and this 6 has came out of it. Okay. So now we can ascribe that this 6 is due to salinity and remaining will be your error. So this is what I want to tell you here is that if you can design your experiment in such a way so that you can classify your data properly into a ANOVA table, then you can extract out the information that out of the total variation, that is this 312, how much can be ascribed to factor 1, to factor 2 or some factor 3, okay, and remaining will which cannot be ascribed to some factor will go into the error component, okay. So now this MSSE, this error will be equal to this 12 divided by this 4, this is will be 3. So this FT will be 49 and this FC will be 3 by 3 equal to 1. Okay. So now we will be taking up the inferences. So now it is correct. That is at 2 and 4 degrees of freedom. 2 degrees of freedom and 4 degrees of freedom. So this is 49 is greater. So we can say that shrimp yield differs with temperature. But this value, particularly for salinity, this is equal to 1, which is far lesser than the 10.649. Therefore, our null hypothesis is accepted and we can say that there is no difference in the shrimp yield due to salinity at 5% level of significance. Okay. So, in summary, we can say that the shrimp yield was affected by the salinity, whereas it was not affected by the, it was affected by the temperature, but was not affected by the difference in the level of salinity. Okay, that is difference in the level of salinity appears to have no effect on the shrimp at all, right? So pairwise test, we will apply the pairwise test only to that factor for which the F test is significant. So we will not apply this pairwise test for salinity. We will be applying this pairwise test for only for your temperature, which we have already discussed with you in your previous section, that is previous session. So this will remain the same, and for salinity we will not conduct this pairwise test. If, say for example, uh, there is difference in salinity, then we will go for the pairwise test, right? So basically this completes your analysis of variance. And what I want to tell you here is that why this uh, analysis of variance is very important for any investigator is. Say for example, for any event that is happening in nature, you observe something, right? And generally we ask question with each other that why this thing is observed, okay, and in your routine discussions also you assign some factors there, okay. Say for example, I will tell you that two students are talking and one will say that say for example x y or z student is securing very good marks continuously and his performance is very good. And say for example, or if we take a example of one cricketer, okay, so one may say that this particular this Virat Kohli or Sachin Tendulkar is obtaining very good score, okay. So the other will may assign some factors to it, He may say that Sachin Tendulkar is he's having God gift. Okay, then he practice well, he has good temperament, he has a very good style. Okay, so in our general routine also, in our life also, for any event, let it be anything, forget about the milk yield or other things, whatever is happening around us, there are some causes to it. Okay, and these causes you can identify with your knowledge from the childhood. That is, as we advances in our age, we come to know with our experience that this thing happens because of this thing. Okay, now say for example, any observation may have number of factors. any observation any observation may have number of factors, those are responsible for it. Say for example, factor 1, then factor 2, then factor 3, and so on. Okay, so basically this analysis of variance, by designing this analysis of variance, you can tell that out of this factor, which factor is significantly affecting this observation. And that too, that is, if some factor is affecting by chance only, then that will not come out to be significant. That will be not be the value will not be above the 5% level of significance. Okay, so that means that you can extract out that out of 10 causes what people are quoting for a particular event, this and this event is actually significantly affecting this observation. And even in that also, the value of f will tell you that which factor is more robust as compared to other, so you can rank them also. So this is the beauty of analysis of variance. You think of any phenomenon, anything in this world. Okay, and if that is a measurable quantity, you assign any number of factors, you group that data into those groups. Okay, make your ANOVA table. Nowadays softwares are available, you can apply 1,000 factors at once, and those 1,000 factors you can get the different level of variation that is being caused by those things. And out of those you can now find out, reduce your data, that these are 1 2 3 are the main factor that is causing this thing. You are going for Mangalyaan, and people are the scientists are using these techniques. That is, this temperature may affect this, this thing may affect this, factor may affect. So then they apply these statistical analysis and find out that what are the most important factor that is affecting a particular thing. And that is possible through analysis of variance, and that was discovered by Sir Ronald Fisher, and that is why he has been given the uh, is called as a sir, and he is one of the greatest scientists, and his contribution is immense in the field of statistics. So this ANOVA is everywhere around us. That is, any observation you make the groups, you assign the factors, you can find out which is the true factor that is affecting that particular observation. So that's all from my side. And as I can see that there are no questions in the chat box, so I am just closing my lecture for today. And tomorrow we will be taking up in the class that is the non-parametric test. Now we have completed all the parametric tests available. Okay, thank you.